So the last thing I want to do is I wanted to review finding distance on a coordinate plane because this is the same thing as finding the length of a segment on the coordinate plane. So when we talk about distance on the coordinate plane, it's also the same as length of a segment on a coordinate plane. And you've seen this before. You've done this in Algebra 1. I just wanted to review it. There are kind of two approaches that are shown in Algebra 1. One approach is to go ahead and graph our points. So if I want to find the distance between 7, -2, and -3, 3, or in other words, the length of segment HI, which I could write as HI without a symbol, I could graph 7, -2, here's H. I could graph -3, 3, here's I, and we would connect those points. And then we'd say, well, let's make a right triangle here. So I would go over and then here, and I have a right triangle, and I can see, okay, this is, and you're counting boxes, not lines here. So that's 1, 2, 3, 4, 5 units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. And I can use the Pythagorean theorem then to find C, the hypotenuse. So 5 squared plus 10 squared equals C squared. So that's 25 plus 100 equals C squared. 125 equals C squared. C is the square root of 125, which if I simplify that would be 5 square root of 5. Or if I went ahead and let me pull out my calculator here, hopefully my batteries are charged. We're going to find out. Yes, they are. And type in the square root of 125. I'm going to choose to round this to 2 decimal places. This would be about 11.18. And that makes sense because it should be the longest side. And since it's bigger than 5 and 10, I get the longest side. And so here is the length of HI. We do also have a formula for this because sometimes it just takes too much time to draw out a graph, draw a right triangle, figure out the lengths of each leg of the right triangle, do the Pythagorean theorem. And our formula actually is just a shortcut for that because it does all of this work of the Pythagorean theorem for us. And what we would be writing is the length of HI is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. The little tiny 1s and 2s next to the x's are called subscripts. They are not doing any math for us. They're allowing us to tell the difference between the different x and y coordinates of our 2 points. So I pick one of my points, I'm going to call h, and say that this is x1, y1. So 7 is the x1, which is my x-coordinate. The y-coordinate, -2, is going to be my y1. And then I'm going to say that -3, 3 is x2, y2. It doesn't matter which one I call point number 1 and the other point number 2, as long as I'm saying, okay, one of them has x1 and y1, the other has x2 and y2. And then I just plug in these values. So I'll have the square root. x2 is -3 minus x1 of 7. And y2 is 3 minus the y1 of -2. If I start simplifying, I have -10 squared. There's a 5 squared. Please note, because I'm squaring a negative number, on our calculators, if I square a negative, I have to put the negative number in parentheses and the squaring outside. or it's going to cause problems. And that's one of those, when we're in person, I'll explain a little bit more. But the way I have it written is the way it would need to be typed in our calculator to get the correct answer. Well, negative 10 all squared is 100. 5 squared is 25. And I have the square root of 125, which if I simplify it is 5 squared root of 5. Or if I type in my calculator and get a decimal, is about 11.18. And there is my same answer. I'm actually doing the exact same amount of work because if you notice, I've got 100 plus 25, which is up here. And then I had to take the square root, which I had to do here. This is really the Pythagorean formula if we got c by itself before we plugged everything in.